Okay, so here we are at the end of Unit 4. We've talked about land use, we've talked about freshwater use, and now we're going to talk about ocean water or marine use. Marine and coastal systems and resources. Okay, so we're going to briefly look at the physical, geographic, and chemical aspects of the marine environment. We're going to look at, this is a huge one, the second one, we're going to look at the impact of oceans on climate and the impact of climate on oceans. We're going to look at marine ecosystems and marine pollution. We're going to look at ocean fisheries and why they've declined. And we're going to look at, just like we looked at protected areas on land, we're going to look at protected areas in the water because there are actually marine protected areas. So the case study, this is very interesting. The Great Pacific Garbage Patch is 1.6 million square kilometers in area, and it's a whole bunch of plastic that's floating in the North Pacific Gyre. Gyre, by definition, is a circular rotation of ocean water that's influenced by wind patterns and the presence of land masses. So we are going to take a look at gyres on our map in the classroom and then in here too. Charles Moore first saw it during a across the Pacific yacht race. It's one of 5 around the world that is contaminated mostly with plastic. So if you take a look, plastics entangle wildlife like turtles who need air to breathe. Plastic never completely breaks down, so there's always microplastic that washes up on beaches. Organisms ingest it and they die. And these are ways that we can prevent oceanic plastic pollution by putting barriers up to catch it before it makes its way into the bigger bodies of water. It degrades really slowly, and it builds up in these continental shelf areas. So the 5 oceans are all connected. They have separate circulation, but what happens in one will influence what happens in the others. The oceans cover 71% of the Earth's surface. They occupy most of the hydrosphere. They influence the atmosphere and the lithosphere, and they encompass much of the biosphere. There's a lot of life down in the oceans, not just on the land. The ocean floor contains, the floor is not itself is not flat, okay? There are underwater volcanoes, right? So there's volcanic activity under the ocean. There are really deep canyons, and the deepest part of the Earth is the Marianas Trench, which in some areas is deeper than Mount Everest is high. So you can take Mount Everest, which is like 6 miles tall, and you can put it down in certain parts of the Marianas Trench, and you will still have a mile of water over top of the mountain, okay? So it's super, super deep. We've been down there too. There are maps that show bathymetry, which is depth, and topography, which are these physical features, the mountains and trenches and stuff of the ocean floor. So we briefly take a little look at what's going on here. The continental shelf is relatively flat, and it's next to the continent, so it's a shelf that's continental, right near the continent, and the water is pretty shallow there. There's where a good chunk of the life exists, is on this continental shelf. The shelf slope break is where the shelf literally breaks. It's the steep drop off towards down the continental slope, down to the deeper part of the ocean, which is called the abyssal plain. Okay, typically wherever you have reefs or volcanism or these other processes that create shallower water, you're going to have a whole lot of life that exists. So you're going to get really productive fishing in the continental shelf here and in these areas around volcanic island arcs where the water tends to be shallower. So ocean water is mostly water, 96.5% water, with 3.5% as being salt. That salt comes from runoff. So as the water runs over rocks on the land, it concentrates into the ocean, right, to make those salts. It brings the ions to make those salts. As seawater evaporates, right, or turns into ice, that salt is left behind. So the water that comes out of the ocean, either through freezing to make ice or through evaporation, is fresh water. And it varies from salinity. The saltiness of the ocean varies from place to place. At the equator, precipitation levels are high, so the salinity or saltiness is lower because the fresh water that rains in dilutes it. You tend to have higher latitudes towards the poles. It tends to be saltier because the ice forms and leaves the salt behind, or evaporation is higher. And coastal waters, down the shore, are less saline because they're influenced by rivers and freshwater runoff. There are nutrients, nitrogen and phosphorus, exist in seawater in trace amounts. They do play a role in those biogeochemical cycles that we looked at previously. Ocean water also contains dissolved gases, which are really important. 36% of that gas is oxygen. That's produced by plankton, plants, and other photosynthetic bacteria. That oxygen is really important because much marine life, fish, octopus, that kind of thing, they take that oxygen, they draw that oxygen out of the water over their gills. Okay. Carbon dioxide is also soluble in ocean water and can turn the water more acidic, which we'll talk about in a little bit. So sunlight doesn't penetrate very deeply into the ocean water. So as you go deeper down into the water, temperatures get colder. Colder, saltier water is the most dense. Okay, it's denser, so it tends to sink. Warmer, less salty water is light, and it stays towards the surface. It's less dense. All right. So heat from the sun, solar radiation getting into the ocean, and wind agitation really create a pretty uniform body of water for about the top 150 meters. It's all about the same density, right? Same temperature, same salinity for the most part, okay? You get below that, and then you get a really rapid change in density, a rapid change in temperature and salinity below something called the pycnocline, okay? Pycno means density, okay? The pycnocline itself makes up about the area above the pycnocline makes up about 18% of the ocean's water. Below the pycnocline, that water doesn't change very much, okay? You don't get wind, sunlight, storms, or really many temperature fluctuations, okay? Ocean temperatures tend to be more stable because they are susceptible to this high heat capacity that water has. You guys know that if you go to the shore in the fall, the air temperature is cool, but you get in the water and it's warm, right? Whereas if you go down the shore, after prom or Memorial Day, the air temperature is warm, but you get in that water and it's freezing. That's because water takes a lot of energy to change its temperature because you have to break those hydrogen bonds between the water molecules. So it takes water a lot longer to warm up and cool down than it does land. So we talked about a gyre, okay? River-like flows of water in the ocean are called currents, okay? And they're driven by density, heating, cooling, gravity, and wind, because water can move vertically through the ocean as well as horizontally across the surface. So if you put currents that move together in a circle, they call it a gyre. So let's look at the Pacific Ocean over here, right? The California current comes down, turns into the North Equatorial Current, turns into the Kuroshio Current, turns into the North Pacific Current, and back to the California Current. So this is the North Pacific Gyre, okay? There's one in the Southern Pacific Ocean. It's the Antarctic Circumpolar Current, which turns into the Peru-Chile Current, which turns into the South Equatorial Current, which turns into the East Australia Current, okay? So these are the gyres that we were talking about before. So the Great Pacific Garbage Patch is somewhere in here. So currents influence climate, nutrient distribution, and pollution. If water flows, stuff in the water is going to flow with it. So if you have a whole lot of nutrients, okay, those nutrients are going to spread. Pollution is going to spread too. The Gulf Stream, okay, the Gulf Stream comes up from the equator, so it's pretty warm, right? And then it takes warm water across to Europe, right? They don't get a whole lot of snow in the United Kingdom, in Great Britain, because of the moderating effect of this Gulf Stream and the North Atlantic Current. Surface winds also create these vertical currents, right? As you have wind that blows north from along the coastline, right? From the north along the coastline. So from, in this case, it's the California coast. There's winds that blow roughly from north to south. It pushes water, this thing called the Coriolis effect we're going to talk about in the key points. It pulls water offshore, which leaves like a gap in the water, so water comes up from below. So this water is cold, it's rich in nutrients, it's high in oxygen, so it produces this upwelled water fills the place. If it's full of nutrients, you're going to wind up with a high amount of productivity. Okay, so that's kind of important. So where surface currents diverge, where there's like a hole in the surface water, that is where upwelling takes place. If you have water piling up where surface currents converge, that water is going to sink down to create downwelling, which brings warm water down beneath and takes a lot of carbon dioxide out of the atmosphere. Thermohaline circulation, thermo is temperature, haline is salinity, is this worldwide current system that moves water from place to place and influences climate in a lot of regions. So we'll talk about that in a second. Here's a great picture. So here we are, right? We've got the north equatorial current is this warm surface current. And the Gulf Stream, right, it moves across to Europe. And as this Gulf Stream gets up towards the poles, it starts to cool, right? The heat from the water is released to the atmosphere, which changes the temperature of that water. It becomes colder, right? And it also starts to freeze. As it starts to freeze, it becomes dense, more salty, right? Because that water is coming out, leaving the salt behind. So you've got a cold current, right? Because it has lost heat to the atmosphere. That's really salty. So it sinks, okay? Downwells and creates this underwater body mass called the North Atlantic deep water. So it allows this water to sink. And then it becomes subsurface, cold, deep currents. And then they come back to the surface and keep moving. So all of these currents are interconnected. We'll talk about how this is disrupting this flow. We're going to talk about what's happening to cause this flow to slow down. This is a big idea. We're definitely going to revisit this again in more detail in the key points, but it's the El Nino Southern Oscillation, or ENSO. It's changes in atmospheric pressure, sea surface temperature, and then therefore a resulting change in ocean circulation in the equatorial Pacific. Okay, so normally there's a wind belt, therefore a current belt that moves from the eastern Pacific over by Peru across to like Australia and Indonesia, right? So the wind keeps pushing in this direction, so the water keeps pushing in this direction to create this mound of water over here, warm water on this side, right? So there's a hole, so to speak, over here. So cold water comes up to fill that gap. So you've got really warm water over here, over by Australia and Indonesia, Papua New Guinea, and colder water over here. So this is upwelling. This is a lot of productivity. This is under normal conditions. You've got great fishing like anchovies and smelt come from this part of the world, right? And over here, because you've got warm water at the surface, it tends to evaporate. So you get higher amounts of precipitation, right? So this is the idea of convection. Okay, let's look at what happens. So El Nino conditions, okay, when these winds that were blowing in this direction, okay, the equatorial, the trade winds, when they slow down, right, they don't blow as hard in that direction, they slack. All of that warm water slides back down the hill towards Peru, okay? So when that happens, there's not as much upwelling. The ocean water warms along the equatorial region towards the east, towards Peru. When that happens, you get precipitation in different spots. Most of the precipitation was over here before. Now it's like in the middle of the ocean over towards California, right? You get a lot of really bad storms over there, and as a result, you get drier weather over here because the warm water is not here to evaporate. So when these winds slack, the water slides back and you get warmer conditions over here. La Nina, and we're going to talk about this in the key points because I like the diagram I have in there, are when those winds blow harder. Okay, so the cold water rises to the surface and moves further west. So it's an extreme circumstance of normal conditions. Currently, we think that these cycles are happening every 2 to 8 years, but we think that changes in climate and sea surface temperature as a result of climate change are making it happen more frequently, and the differences between El Nino and La Nina are more extreme. Until the Clean Water Act, point source pollution was really from trash and sewage from cities. It was really common. People would, instead of going to landfills, people would, municipalities and stuff would take their trash to a port and dump them on a barge, and they would take the barge out to sea and dump the barge in the ocean. But now, because of the Clean Water Act, most of that pollution is non-point source. So oil, plastic, chemicals, and nutrients tend to flow into sewage, sewer grates, and that kind of thing, or run off into smaller bodies that wind up making their way into the ocean in general. Plastic is an issue. It's a big issue. It's fishing debris, trash, plastic bags, all that kind of stuff. Making it not happen is one way that we can really reduce the issue of plastic pollution. Banning plastic bags is one of the ways that it has started. 90% of the plastics that make their way into the ocean come from 10 river systems, mostly in East Asia, South Asia, and Africa. A lot of it comes from the Yangtze River and the Yellow River and the Hai He in East Asia. Oil pollution comes from all different sizes of spills. I clearly remember these two, the Exxon Valdez, which ran aground in Alaska in 1989, and then Deepwater Horizon. A platform exploded and sank into the Gulf of Mexico, and they couldn't cap the leak deep in the bottom of the Gulf of Mexico for months and spewed millions of barrels of oil. But most of the oil that gets into the ocean comes from natural seeps in the ocean bottom. Okay, so the seepage is diffuse, so the impacts are not quite as large. So the Exxon Valdez, when that ran aground, we improved our response techniques, and then we changed legislation, as humans tend to do, to require that all tankers in U.S. waters be double hulled. So the hull of the ship is the thing that separates the inside of the ship from the outside of the ship, and then prevents the stuff on the inside from leaking into the outside. The Exxon Valdez was a single hull ship, so it was one layer. So this legislation required that there were two hulls. So there's the inner hull and then a space and then the outer hull. It's like double walled in essence to prevent, to reduce the risk of rupture when a tanker runs aground. So we talked about this, and we talked about the ecology stuff. Toxic pollutants like mercury and lead will accumulate in fish and shellfish, which makes them unsafe for people to eat. Mercury comes from burning coal and from mining tailings for the most part. And we talked about mercury bioaccumulating and then biomagnifying. It accumulates in the tissues at higher concentrations than it is in the environment. And then as those organisms get consumed up the food chain, it magnifies at higher trophic levels. So when I was pregnant with my daughter, I was limited to the amount of tuna I could eat. I was allowed 4 ounces every 5 days. So of course, I wanted tuna all the time. But they told me I could only eat the chunk light tuna, not the albacore tuna, because it tends to biomagnify more, the mercury biomagnifies more in the albacore than it does in the chunk light tuna. It's a lower quality of tuna, which was fine with me. I just wanted the tuna. Because if the mercury got into my system, it could have impacted my daughter's neurological development. We talked about eutrophication again and again and again, but here it is. We talked about the dead zones and the algal blooms. Sometimes when these algal species bloom, you can get this thing called a red tide. So the tide is literally red because these are organisms, dinoflagellates, that produce red when they reproduce. They turn the water red, and sometimes they produce toxins which can kill fish, and they won't let you swim in the water because of these poisons. Okay, we need to talk about pH before we get into ocean acidification. So in any aqueous solution, this is as deep as we're going to get in chemistry, water molecules will split into hydrogen and hydroxide, okay? Pure water, H2O, has an equal concentration of hydrogen and hydroxide, right? Because water is H2O. Here's your 2 H's, and there's your O, okay? So pure water has a pH of 7. It's considered neutral. If you have a substance that breaks down and produces more hydrogen ions than hydroxide, we call it acidic. If it produces more hydroxide ions when it breaks down than hydrogen, we call that basic. So pH scale talks about the relative amount of hydrogen and hydroxide ions that are released. Okay, so water has a pH of 7, it's neutral. Okay, if it produces more hydroxide ions than hydrogen ions, we say that it's basic. If it has a pH above 7, it's basic, right? If it produces more hydroxide ions, hydrogen ions than hydroxide ions, it is said to be acidic. It has a pH below 7. Okay, so you got to make sure that's clear in your heads. It's a logarithmic scale, which means that a difference between a pH of 0 and 1 is a 10-fold concentration. So normal rainwater is 10 times more acidic than neutral water. Okay, I hope that makes sense. So this idea of climate change, it's really changing ocean chemistry. Which is then causing lots of issues. So the ocean absorbs carbon dioxide from the atmosphere as part of the carbon cycle. The ocean is a natural sink for carbon, right? It's a giant sponge for carbon out of the atmosphere. So about 1/3 of the human-generated carbon dioxide that we have created since the Industrial Revolution has made its way into the ocean. But there's a tipping point, okay? The sponge will fill. There will come a point where the ocean will not be able to take up any more carbon dioxide. So if there's no more carbon dioxide going into the ocean, then that carbon dioxide is going to remain in the atmosphere to intensify global warming, okay? We'll talk about that in a few chapters. As the ocean absorbs more carbon dioxide, it causes ocean acidification, okay, where the pH of the ocean water decreases. It becomes more acidic, which makes it harder for sea creatures to grow shells, right? It's that, like we talked about at the Rosemont Cemetery, we talked about the fact that limestone, right, which is calcium carbonate, which is what most shells are made out of, breaks down in acid precipitation, just like a Tums breaks down when you've got heartburn and you chew it up, okay? It neutralizes the acid in your stomach, which makes you feel better, okay? The same thing happens to seashells and the creatures that secrete them as part of their home and their niche, okay? They won't be able to grow the shells, so they won't be able to survive. All right? And that's the idea where the shells are going to dissolve faster than they can be formed, right? So you lose the higher the amount of carbon dioxide in the atmosphere, pre-industrial, 2007, and sometime in the future. We're over 400 ppm right now, parts per million carbon dioxide in the atmosphere. We're going to have reefs shrinking more than they are growing, more of this darker red orange than the blue, okay, than this lighter blue. So we're also overfishing. Okay, if you look at per capita, per person consumption of seafood, you have a lot of that in some of your, in these red regions, Greenland, Iceland, Portugal, etc. Okay, and demand varies by region. You know, the central parts of Asia typically and Mongolia typically don't eat a whole lot of seafood. So, about 60% of our world wild marine fisheries are fully exploited. We can't take any more out. We can't pull them out at any greater rate without depleting them. So we can't sustain them if we keep fishing them. In the 1800s, 1700s, we started to develop this idea of industrialized fishing, where you use big nets and big processes to take in big quantities of fish, okay? So we have been overharvesting the oceans for a very long time. As we moved into the 20th century with big ships, we caused a lot more of these fishery collapses. So these are some of the industrialized fishing techniques that we use that you need to be able to explain. So the first one is purse seining. If you've ever watched Finding Nemo, the original, not Finding Dory, Finding Nemo, this is where Dory gets caught, or Nemo. One of them gets caught. I think it's Dory. When they finally all get back together. So they take this big net around a column of fish at a surface, and they pull it up like a drawstring, okay? And they catch everything that fits in that net. Drift netting, they lay out these really long lengths of net in order to trap species that go over open water in really big schools. Long line fishing is how they do most tuna. And if you've ever seen The Perfect Storm, this is how they fish. They put out long lines, that's why it's called long line fishing, of hooks, baited hooks, and they catch fish that way. And the other idea is trawling. So trawling, they take this weighted cone-shaped net and they drag it through what they call the pelagic zone. It's not the surface and it's not the bottom, it's in the middle. But sometimes, depending on what they're trying to get, they do bottom trawling. So they have these really heavy nets weighted down that get dragged across the bottom to catch bottom-dwelling species or benthic species. We're dealing with a lot of these issues and the collapse of these wild marine populations as a result of overfishing. The case study for this chapter used to be on the Atlantic cod, how it was overfished to the point where, there were very, very few left, and they wound up closing the fisheries for a while. They did a lot of bottom trawling, which destroys the benthic habitats that the cod tend to inhabit. So by 92, they closed all of these areas to fishing. And the cod species are coming back, but not very well. All cod fisheries were banned. So they closed a huge amount of fishing area for cod. So if you look at the advent of industrial trawling, how the cod population spiked, how the harvest spiked, and then eventually how it collapsed, right? And you can look at the harvesting in thousands of metric tons from this one area in particular, the Grand Banks. So one thing we do to ease the pressure on wild populations is this idea of aquaculture. So you raise fish, seafood, and other forms of marine life for human consumption. So it's fish farming is what it amounts to. And these are the kinds of things that you can raise. Crustaceans, mollusks, aquatic plants, etc. As we are doing aquaculture, we are also fishing down the food chain. So we are fishing smaller fish, we're fishing younger fish, and we are fishing for targets, other fish, species of fish that are further down the food chain, and they're also more abundant. But they're really not the kind of fish you would think you would want to eat. The orange roughy, if you go to a restaurant and orange roughy is on the menu, it used to be called a slime head because it had these unique mucus canals in its head. You go to a restaurant and you order Chilean sea bass. It sounds a lot better than ordering toothfish, okay? Chilean sea bass is not a bass. It actually looks more like an eel. So they rebrand and remarket these fish names so people will want to eat them. And we are overfishing them. So we're having to fish further and further down the food chain. So all of those methods of industrialized fishing, the purse seining, the drift netting, etc., the bottom trawling, all create something called bycatch. Bycatch is when you haul in species, when you harvest species that you're not meant to harvest, okay? Dolphin, when they were fishing for, the Japanese were fishing for tuna in the late 80s, early 90s. I remember seeing this when I was in high school. They were fishing for tuna, longline fishing, and they would pull up dolphins onto the deck of the ship. And instead of putting them back in the water, they would let them die on the decks of the boat. And it was a huge outcry, a huge outrage, and a boycott of the tuna industry for a very long time. Now a lot of the tuna, when you read a can of tuna or a pouch of tuna, it says dolphin safe because they've changed their methods. So bycatch is anything that you catch that you're not intending to catch. So a lot of it is bycatch. And they've made changes to international fishing law to reduce bycatch. So drift netting is now banned. Bottom trawling, there's the Georges Bank where they did bottom trawling for cod. Not only do you increase the bycatch, but you destroy these underwater benthic ecosystems. You've got the rock and the urchins and all these things living there, and you take this huge giant weighted net and you drag it across. Of course you're going to destroy it, okay? This is what trawling looks like, what the benthic area looks like after trawling. It is definitely extremely different. And one thing that's helped increase the cod population is that these benthic ecosystems are coming back. They're regenerating, going through underwater secondary succession. Because we are overfishing, because we have a lot of pollution in the water, because we are changing habitats, partially due to climate change, we are depleting biodiversity that threatens normal ecosystem services that take place in marine ecosystems. So there's less production, right? So there's less oxygen that winds up getting produced, primary and secondary production. So then that impacts the fisheries in the ocean, right? If there's less oxygen in the water, you're not going to have as many fish that are going to be able to survive, right? These organisms, these ecosystems are going to be less capable of withstanding disturbances, any changes, human-induced or natural. They're going to be less resistant and less resilient. And then filter feeders are not going to be as capable of purifying the water because there's just too much stuff in it. So we can set marine protected areas, much like we set preserves and stuff on the land, that don't allow oil drilling, but they allow for fishing and that kind of thing. So there are areas, these purple areas, about 3% of the ocean's waters have that designation. So you can't drill, but you can fish, right? So they're protected areas versus a reserve where you can't fish at all, okay? You can be on the edges, but you can't be in it. So if you're a commercial or recreational fisherman, you don't like that area. But as a scientist, they tend to argue that, no, that's really good because you protect them inside and then they swim out and then you can catch them. A marine reserve doesn't allow fishing at all, okay? So you can think of that as where you allow the fish to grow, right, and develop, which is reducing habitat destruction, and you are improving the diversity and productivity and the biodiversity in these marine ecosystems. All right, we have finished land and water use. And so we're done with Unit 3.